Howdy, everybody. Ooh, uh, I'm 45 years old, and apparently my voice still cracks. Hopefully, you're having a wonderful day whenever you are, though. Um, I don't know what else to say about this day, but LOL, I guess. It's kind of a trolly day. I suspect, I believe his name is Eric, is like grinning ear to ear. I haven't checked any of the Reddit solutions or the Reddit threads yet. I have them popped up here so they're ready, but I haven't looked at anything. But I suspect he's grinning ear to ear because he got us all. And I will maybe to clarify too, I think you can, if you understand the problem and the constraints of it from like the computer science perspective, I think he designed the solution and the input in such a way that it would lead you down a path. And I actually think that's a cool thing for a puzzler to do. So it makes like it feels very trolly, but at the same time it feels like the hints were there that it led you down a path to solve the problem in an unexpected way, I think is the way to say it. At least I presume. It's quite possible that other people don't have the same input as I do. I'm highly suspect that that's actually the case, and we'll talk about that in the, there is no part 2, but we'll talk about it in like the quote unquote part 2 of this video. We'll actually solve the puzzle. I'll show you how it solves, and then I'll show you like why it's actually hard, even after I spent some time trying to do some optimizations and stuff like that. So anyway, let's just get to the day. So it is day 12, Christmas Tree Farm. It's the last day, by the way, so we finished with a banger. At least in my mind, this was a fun one. And it's kind of sad that we're done. I have lots of fun things though planned, that working more with the Z3 solver, going back to puzzles we haven't solved, so there's lots more content. If you have preferences though, put them in the comments. Otherwise, I mean, let's just talk about the day. So what happens is you fall down a chute and you land at a Christmas tree farm, and there's a bunch of presents, and the elves are frantically trying to put the presents under the trees, and the presents have specific shapes. And so they're trying, and each tree has a limited available region to put them in. And so the question is like, can you put there's also a requirement of like how many presents to put and what type of presents to put under each tree. And so the question it's asking is, can you find if it's possible to put the list of presents under each tree that's expected. That's what it's asking you. So it gives you the examples to do this. If that wasn't a great summary of the explanation, it's going to give you each present and its shape, where the hashes are the shape of the present, and the oh sorry, let me just check for a second. Okay, so the hashes are like the shape of the present, and the dots are like the open area. Like, so that's to say there's like some gaps right here, if that makes sense. And so for this present, there's gaps right here. There's gaps right here. For this present, there's a big gap right here. For this present, there's like edge gaps. So you're going to get a list of presents for the input, and then you're going to get the tree regions. So in this one, it's saying there's a 4x4 grid, and you need to place presents 0, 1, 2, 3, 4 twice in this grid. So it's saying, can you place present 4, which is this one, twice in a 4x4 grid? And you have to ask yourself, is that possible? Okay, and you need to do it for each of these, right? So it goes through the list. It goes through the example, right? It describes all this stuff, but it goes through the example. So it says, imagine you have this like 4x4 grid. You need to determine if you can fit 2 of these like this, right? And if you've ever done these type of things, like there's actual puzzles that are like this where you're given a bunch of shapes and it's like, can you fit them all into this like grid or whatever? And some of them are like really simple that you're just kind of placing and rearranging. Some of them are tricky where you have to like set a piece to be like at 60 degrees or whatever, and then you can fit the rest of them in around it. Anyway, the point of all of this is to say, you could probably pretty easily in your mind determine like, oh, here's some ways that I could do it. For a small sample, I would say. When the samples get very large, it becomes much harder. Anyway, the point, what they say is, okay, well, what you can do is if you like actually take this shape and flip it this way, and then bring it down, you can see you can get this A is one shape and this B is the other shape. You can get it to fit in the 4x4 grid. So since you only need those two, you can definitely do that. The second region, even though it has many more things, you can definitely still get them to fit. And you can kind of do the math and like kind of put them in there and try and solve them, right? The third one doesn't work though, and notably the difference between the second and third is you need one additional of this shape right here, right? And so there's just no way for you to like, you can do all kinds of things, but you can never just place that last piece anywhere in the grid. And so what it's asking you is, how many of these grids are like possible to solve, right? Given a region and given the number of each of the presents, how many of them are possible? I think is maybe the best way to say it, is like it's just saying how many of them are possible. Okay, if you've done problem solving before or computer science, you've probably heard of this problem. It's a cousin of the knapsack problem. And I actually don't think I brought this up. So this is a common problem. It's called the knapsack problem, and it's an optimization problem. So the optimization problem is saying, hey, given a knapsack that can hold so much weight and some things to put in the knapsack, what is the optimal amount of stuff to put in there to like maximize your money? There's other problems too that are like similar to this, right? They all kind of fall under this category of like a satisfiability problem. This one in particular though is called a 2D packing problem. And so this is a cool article that may be worth reading. I'll include it in the links. It's a review of some of the recent work that's been done on trying to solve this. And why is it interesting for people to try and solve this problem? Because it's one of the NP problems that are particularly difficult. And we won't talk about P versus NP too much here, but suffice it to say is like the bin packing problem. And this is like a specialized version of the bin packing problem where it's just like a 2D packing problem. But these type of problems are known to be very hard to solve. And so they're easy to verify, but very hard to solve. In fact, I even think it says in here, it's currently recognized as an NP problem, which is mainly solved by heuristic algorithms. So that's a key here. You should say to yourself, okay, when you see that it's an NP problem, essentially what it's saying is, at a high level, there's not much more you can do than just try all the solutions. That's not technically the case. So if you're a computer science nerd, I understand that's not technically the case. But at a high level, that's essentially, or at a very, very general level, essentially is what it's saying is, there's no optimal way to do this, but then to just try all the ways. With the exception of, you can maybe like find some heuristic that might lead you to a solution quicker, okay? And this is interesting because we should be clear what we're asking here. We are not asking what the optimal solution is, right? um the question is like, that's a whole nother question, right? There's one question where you could say, like, given all of these presents or these 2D grid, these 2D objects, what's the smallest amount of space I can put them in? That is a different question than, or what is the best way to fit them in this thing? That is a completely different question than, is it possible to put it in there, right? And so the is it possible is an interesting problem. Obviously, if you're able to use some cool solving to like figure out quickly if it is possible, that's extremely helpful. Um Otherwise, you have to recognize that you're probably going to have to search the entire search space to figure out if it's possible. Okay. So why am I telling you all of this? Here's the actual PDF too. You could download it and read the details. It's very interesting, and we'll actually talk about it a little bit more. But you can see, like, uh, when you look at this, you say, "Oh, this is kind of what I'm trying to do." Right? I have some shapes, and I'm saying how hard would it be to pack these into a given amount of space, right? Okay, we will talk about more, but why is this important for getting to the solution in part one? Well, if you know that it's like a hard problem to solve, the first thing that you should start looking for when you're trying to solve a problem is, well, how can the inputs, or can the specific inputs lead me to a heuristic that that makes it easier to solve, maybe, is the way to think about it, right? So you say to yourself, oh, is there some kind of thing that makes it easier to solve? And so you can actually see, I guess you can already see here, is there's two very simple cases that you can ask yourself when you're trying to solve this puzzle. And that's where we'll start the drawing here. So hopefully you don't mind me drawing a lot like this. But oops. Go here. That. And then start. Okay. So let's imagine you have to like fill up this grid, right? And let's just do simple boxes right now, right? We'll say the shape you have to fill is a whole 3x3 grid, right? And let's say that this grid is I don't know, 12 by 12, right? Well, one simple question you can ask yourself is, are there enough 3x3 grids here, right? So if I turn this into what is that? Is there's going to be like 4 of them, right? Okay, that isn't very well drawn. I apologize. But what does that mean? It means I can never fit more than like 16 of them in there. So if my query is, can I fit 5 times the 5 times the box, right? I can simply just ask myself, well, can I fit 5 in here? And since there's 16, the answer is yes. Well, what if I have another question where I say, well, can I fit 24 of them? Right? Can I fit 24 of them in here? No, I can't, right? I'll never be able to fit those. So, not going to happen. So this is a pretty easy, quick check, right? And what I mean by this is that's what the easy is over here, where I get like the number 425, is I just say ignore the corners, right? The actual 3x3 block will look something like, one of the shapes was like this, right? And then another shape looked more like this. this a little bit. Okay, it doesn't actually matter what they look like. I can just turn them into 3x3 grids like this, right? And then just say how many of these can I place in there. And so if the puzzle says I want to place 5 in total and there's 16, then I know I can place them. It doesn't matter the arrangement. Again, remember, we are specifically just asking ourselves, is there a solution? And so if it's asking me to place 5 and there's 16 of these spaces available, well, now I know, yes, the answer is true. If it's 24 and the 16 is available, well, it's technically not an X, so I should clear that out. It's not an X. What it actually is it's more like a maybe. We're not sure yet. Maybe we can do it. Okay, so that's one check we can do. So the first check is, I'll put it over here. First check is, can we just place 3x3 block? Right? So this is super simple because it's just math. We know each one is a 3x3 grid, and we know based on how long these are, right, how many we could fit in there. And it will still work, right? Like imagine if this was how do I do this? Imagine if this was 13. Right? 13 down here. We know there's a little slice down here that like will never fill up, right? But it's still just math. We know that we can fill it here. Okay, so that's one check. The second check that we want to perform is that what I'll call the area check, right? So if we count the number of grids that are used here, right? Like we do this type thing, like this, right? And so we know this one uses 7, this one uses 7. Maybe there's a very sparse one that's just like this, and it only uses 3, right? Well, we know the total area of this. I've now changed this number, so I have to figure out what that is. 156, is that right? So we know the total area of this. So right here, we know the area is 156. Well, if we sum all these up, and it's greater than 156, then we know we could never place them. Even if we found the perfect arrangement, right, where they fit together very nicely with like perfect interlocking, if there's 156 squares up here and, or sorry, 160 up here and 156 here, we could never solve it, right? So if we say like the area of the box times 5 equals 212, then we know this one won't work, right? This one will definitely never work. But if we go back and we say, okay, the area of the box times 2 equals whatever, 123, now we're back in this maybe category, right? Does that make sense? I hope this makes sense. These are two like quick checks that we can just do with math, right? And so this is what I did when I first started the puzzle. I'm like, okay, well, let's just find out. Looking at the input, there's a lot of stuff, right? Maybe I only actually have to solve a few of them, and then I can like focus on those few and see what kind of heuristics I could use to try and solve it. And I had, as I was writing this code and checking, I was doing lots of thoughts on like what the possible heuristics were. Like, could we create like a larger geometry? So if you look at the input, the puzzle, the number of presents is actually quite large in each one, which should be an indicator again that like this is going to be a hard thing to solve. Because remember, you have to place every present, but not just every present, every rotation and every flip. You're going to have to try all of them essentially to try and get it done. So you have to find some kind of heuristic that's going to help minimize the cases, greatly reduce the search space, okay? So I knew these were going to be large. So part of me was saying like, is like, oh, can I try and find patterns in here, right? Can I say like, oh, these two blocks are like, I can put them all together to form a perfect square. And then I can do that perfect square some number of times. Oops. Get there yet. We won't go to our thing yet. Right? So can you do some kind of large geometry or, are there perfect squares that like I said, I think this is kind of akin to this one. Besides just finding big larger shapes, can you find like perfect squares that you could fit in to try and solve it? Anyway, that was my thinking as I'm going through this. And so I run the actual code. I'll show you the code. So we'll start with the code, right? With some of it. First, I have my input. I have my shape size. I checked. They're all 3x3s. And then I have my coordinates. We'll use those later. Where we get here. Here's where the craziness comes. But I'll show you what I do, right? So I have a shape, which is a vec bool. This is just my 3x3 grid. So I impl from, I calculate the area of the sheet, the shape, right? What is the area? How many of it is like, how much of it is actually covered is maybe the way to say it. And then I have my region parser as well, right? So for each of the regions, I need to split. And then for the dimensions, I need to split by X. Then I can sum those up. So now I have my parser, right? So now if I go down to main, here's the code. This is the actual code. I don't think I've changed this much since I originally did it. I was asking myself how many are easy, how many are just area fails, right? So how many are impossible? So this is how many of this box, right? So this is the this one is the easy, and this one is the area fail. And so what the difference between those is what needs solving, right? So this is these are like, this is the number of solutions that you're going to have to figure out on your own. And I'm like, okay, how big is that? So I went through all of and you can see I haven't actually cleaned up this code too much because of the troll. So I look at this and I say, okay, now how many have failed? How many are easy? How many need solving? And I print that out, and here it is right here. How many are easy? How many failed? How many need solving? That big fat 0 right there. Man, that'll I laughed out loud. Okay, you got me. You actually got me. Yeah, so I think do I say this here? Yeah, I read the problem, I panicked, analyze the input, and then I honestly, he's got to be grinning from ear to ear because he knows that he got us all, I presume. I assume most of us panicked, and I know at least some of us did, besides myself, because I was reading comments from previous videos of people saying, oh no, the day's terrible, how am I going to solve this one? So anyway, how do you solve that then? Well, here's how you solve part 1. And there's only one part today, right? So here's how you solve the day of the puzzle. You just go through all the regions and you ask yourself, what is the available space and how much is needed? how many spaces are needed, and if there's more available space than needed, then that is a valid region. You count it up and you solve it. That's it. You're done. Read the input, people. I should clarify though, this took me some time to get to the LOL, right? Read the problem, I had to do the parsing, and then I was doing the analysis, right? I'm looking at the input, and I'm and this code right here, I purposefully left this in. I usually clean this stuff up, but I purposefully left it in because of the trolliness of the day. So I actually was like playing with this, trying to figure it out, and then that's when I got the need solving 0. So there you go. Yeah, I even think, I don't know that he ever like shares like how many times you tried or whatever, but I think I tried a couple times where I'm all like, wait, because I did actually have a couple bugs in this where it was saying, and I just done the math wrong, where it was saying all of them fail, I think, and so I put a 0. Like I was like, wait, do none of them actually work? So the irony of this whole thing is that the sample input does not solve this way, right? If you run this against the sample input, it will say all 3 of them need solving. So none of them like fit the requirements, I guess is the way to think about it, of the troll. So you actually, if you're trying to solve the sample input and not the puzzle input, you don't get this solution, which I also find hilarious, right? It's like, clearly it happens, okay? So that's the whole thing with this stuff. So what do we take away from this? I think, well, before we get to that, let's actually talk about like how you would actually solve this problem if you were trying. So you can see here, I do have an attempt at just the sample input. You can see after I've done a ton of optimization, it takes 159 milliseconds and it comes back with 2. And most of it, 99.9% of that time, is on the fail case. And why is that? Is because you kind of have to try all of the solutions, right? I could be wrong on this, and I'm willing to admit I'm slightly wrong, but the again, the way that these 2D bin packings work and why it's considered an NP problem is because you kind of just have to try them all. But the way that you can use some heuristics to try and minimize the branching. And that's the whole point of this, right? Is like, or what I want to talk about for the rest of the video. If you go to this thing and you look at the we won't talk about all this because there's a lot of papers that like I think we could do way more optimizations. My 156 is not the smallest, but it is this part right here. So another sub problem involved in 2D irregular packing problems is the sequence optimization of parts during the packing, right? And so what they're saying here is like, how do you pick the next piece, right? Because if you can pick a piece that's going to like reduce your search space for the rest of the problem, it will reduce the number of checks you have to do. So what do I mean by that? And I'll show you my solution in a minute to describe this, but like imagine a particular shape, but we'll call it S1. Let's say that it has like 2 rotations or like 2 variations of it, and you can place it on the board at any moment in time. You can place it on the board anywhere in the board, 50 places, right? Let's say you have another shape called S2. It has 5 variations, but you can only place it 2 places on the board. The question you should ask yourself is which of these should I prefer to test first? Well, if you think about it, this one has a total of 10 tests, and this one has a total of 100, not test, options, right? So if you think about it for a second, choosing the 10 one is probably better, right? Because if you choose the 100 one, you now have to do 100 of those and go through the whole thing. And this is I actually should I is it like early fail analysis? Fail fast principle. And it kind of falls under this category. It's not quite like this fail fast, but the idea is if you pick 10, that you only have 10 checks at the higher levels, right? So if you imagine your search space as like something like this, if you do 10 right here, and then you only do the 100 down here, if you've already solved this 100 problem, like right here, so let's do this. If you pick the 100 problem down here, if you solve this 100 problem right here, and then you experience it right here, right here, right here, right here, right here, well, if you've memoed it, you don't have to do that one again. It is much less likely, though, in the search space of the solution that this 100 problem will show up like way up here, right? Not only that, but it's much less likely that this 10 one will show up down here, right? And so once you've solved this 100 problem, as you've done your DFS of the solution space, and you've gone down here and you've solved this 100 one, you never have to solve it again, right? But and maybe we should use smaller numbers here. This 10 branch has only branched 10 times, though, where this 100 one will have branched 100 times. Many more. And so you kind of want to pick the one faster. It can be hard intuitively because you may say to yourself, well, eventually you have to search all the solutions, right? So you just are going to have to pick them all eventually at some point. But because you're picking the one with like the least options, if you can tell quickly that like this 10 won't work on this chain, it's highly likely that it's not going to work on the rest of them, right? This is especially the case because there's some where there's only 2 of them. And so if you like try down this branch and it says no, and you've memoed all of that work, it's highly likely that the 2 here is going to say no as well. And so you've only done 2 checks here. Whereas if you'd done the 100, you would have had to do it 100 times. I know it's hard to describe, but like it's like a fail fast principle, and it actually helps, right? If I don't do this, it will cause problems. So let's talk about how to solve this problem then. Just to be clear, essentially we have to test all of the cases and say yes, this or no, this won't work, or find some valid case quickly to say yes, this will work. So I'm going to use this kind of like fail fast type approach in the algorithm. Okay. So I'll show you what that looks like. Here's the heuristic, right? Is we say, given a board and the remaining spaces and all of the shapes, I'm going to tell you, can I place this piece? And, I should say we also do a lot of like, pruning, right? So if we ever get to a point where like we can't place a shape, we know we're done with this branch and we should be done and stuff like that. So you'll see that all over the place. But this heuristic is just trying to ask ourselves, what is the shape with the fewest valid placements, the most constrained one? We'll put that one first and then try the rest of the shapes later. So again, the question we're trying to ask is it possible, not what is best? So we focus on minimizing the branching here. And the heuristic is what is the most constrained. So again, how do we do that? Basically, we're going to go through all of the shapes. And for each of them, we're going to determine how many places we could put it on the board. Okay. And so I'm not going to go through the code too much. I do use a bit mask, and so you'll see me using like the masking up here. This was me trying to optimize the heck out of it to get it. It started out at taking 6 seconds, and I got it down to 159 by doing some of these optimizations. I'm not going to talk about all of the code today, just because I feel like it requires like a lot more in depth to like talk about the whole thing, right? So, but I have this count placements, and what it's basically just doing is finding how many places I could put a shape on the board. And I kind of build like a mask to like for an entire row, and then I can check how many it can fit on that row type thing and move it around, right? So I am using a mask, just to be clear. It's a U64, and the board itself is a mask as well. It is a U64 as well, right? This wouldn't work on the actual input. I haven't tried it, though. You'll see I have a comment in there like, should we try it? I don't think it'll actually work because we're using this U64 and we're using this packed value. I just don't think it's gonna work. So it's like a it's like me optimizing the thing. But the idea is like, could you try it on the thing? Maybe, but anyway. Where was I at? Okay, so what is the heuristic then? We go through, we count how many times we could place that piece on the board, and you know, if we ever exceed it, the number of placements that we want versus what the minimum is, we know it's not worth checking. If we found a shape with 0, we know the board is unsolvable, so we return none. Otherwise, we see if we had a new min. And if the new min is 1, we know we're done, so we can stop there. This is all trying to speed up the 6 seconds into like 159 milliseconds. And this is not super optimal, just to be clear, right? So you'll have to be mindful of all of that. I think we could go, what I'm saying is finding a better heuristic might help you solve this better, or finding more interesting shapes and geometries. Like I said, there might be ways to like turn the hard problem into an easier problem by reducing the search space. I don't think that's what the puzzler intended, though, just because of it clearly being, you know, easy versus area. Anyway, the heuristic is going to return which piece has the fewest number of valid placements. So early on, there'll be, you know, some shapes that are like, oh, you could place it 20 times. But as you start getting in the middle area, there'll be big differences, right? Where it'll say, oh, I could place this shape 50 times versus I could only place this shape twice. We prefer to pick the twice one because once we've like cleaned up that branch, we can reuse that throughout the code much more. That's where the memo part comes in, okay? So that's our heuristic. Count the number of shapes and find it, right? So now we have this heuristic that's telling us like which one to pick. Now we just have to DP it, right? So we pick one, try it, and then memo it. This is like the standard DP, right? I should say try rest, right? We pick one, we try the rest of them, we memo the solution, and we do that recursively, right? So here's my DP. It's called DP pack. You give me a board, again, which is a U64, so I made it like, you know, 8x8 or whatever. I guess it works by 12 with 12x5 as well, which is what the input is. You give me what's remaining, and again, I packed this into a U64 so I could memo. These are, now I'm just memoing 2 U64s as opposed to like a vec bool or a vec car and then like a vec of U size. And that actually does help a lot, but it makes it harder to like read the code. But just imagine this board is like the grid, and then the remaining are the number remaining for each of the things. And you can, if you want to look, you can see the math I use up here, right? Is I created a little struct to help me, and I say, I put each of the values in a block of the U64, right? And that works because none of the values are greater than 60 or something like that, and there's no more than 8 shapes, so you can kind of keep it in one single U64. Again, these are just optimizations, but those are the things we need, as well as the shapes and our memo, right? So the first thing we're going to do is we're going to say, hey, have we already seen this before? If we have, we can just return the results. If there's nothing remaining, we're all done. We return true. Otherwise, we call our heuristic and say, hey, what's the next best shape to try and place? And so we try it. If we don't get one, we know we can't solve it from this position. So we insert and return false. We memo and return false, right? If it is, we now have that shape, right? So we're going to try each variation of the shape in each of the positions, see if it can be placed. And then we place it on the board, we decrement that value, and then we DP down further, right? We've talked about DP a lot in previous days, so if you're not sure what dynamic programming is, go look back. But again, the idea is just we break a big problem into a small problem. And in this case, the small problem is try and place the most constrained piece on the board, and then update my state to say I've placed this piece, here's how much I have left to do, and then try and then ask the function to solve that smaller piece. And you'll go all the way down, and then it'll say, oh, I can't do it with this, and you'll go up a little bit, can't do it with that, go up a little bit more, can't do it with that, go up a little bit more, and eventually you've tried all the ways to do it, and you've either found a solution or you haven't, right? If we ever go through all the shapes and we couldn't place them, we know it's false, so we can do it. And then these are just some helper functions. Again, I won't go into them too much, but just because we have a board that's a U64, we have to do some math and some bit stuff to say, can we place a piece, and how do we place the piece? But then, all that's left to do for the sample is to say, hey, parse the input, get all the variations of all the shapes, and then for each of the regions, call the bin pack on that region with all of the shapes. So is this optimal? No, probably not. Is it pretty complex to get to 159 milliseconds? It is, yes. Is the general idea complex, though? I hope the answer is it. I think I understand, or it doesn't have to be, because the heart of the algorithm is right here, right? Is in this pack, right? Where we just ask ourselves, have I already seen this state? And if I have, I can stop. Have I filled up all, have I solved the problem? Then I'm done. Otherwise, try and pick the best shape. And for that shape, try and put it in all of the positions it can go, and then just ask myself, can I place the rest of the shapes that I need to place in this board? That's dynamic programming in a nutshell. That's, I think, probably the best way to solve this. And, there are people much smarter than me right here that have said, this is a really hard problem to solve, right? So if you're struggling to solve it, and don't feel bad, because everyone probably struggled to solve it, and then they came upon hey, look at this, I actually don't need to solve it. It is a tough problem to solve, and there's a lot of math and research. You can see this paper that I'm sharing with you, by the way, is a meta-analysis paper. It's like so just to be clear, this is they have reviewed a bunch of recent or most up-to-date information on the 2D packing problem, and have kind of given you links to all these things. So this isn't just 5 or 6 engineers trying to work on this problem. This is they've worked on hundreds and found hundreds of references that talk about doing this stuff. And so a lot of people have done a lot of work on this and have said this is a hard problem to solve. So if you are having trouble solving it, you're in good company because all these people agree with you, right? Now, that being said, it's quite possible I'm about to go look at Reddit, and it's quite possible that the problem had some more tricks to it that made it solvable. I suspect that is not the case because you can see even me trying here, it just took the sample input. And remember, the sample input only has like, what does it have? One, two, it has 7 total shapes in a 12 by 5 grid, but each of those may have like 3 to 8, I don't know, 2 to 8 variations that you have to try and place. It becomes explosive how much you have to like test, how many regions you have to test before you can say this is just not solved. So in order for you to actually solve this, there has to be something else to the puzzle where you'd say, oh, I can actually make a super shape that's a perfect square. And I can't necessarily see that here. But that would be what you're looking for, is like if you wanted to make this a tractable problem, is what they call it, something that's actually solvable. Like think about it like Tetris, right? Like if you imagine you have a shape like this, so that's not a good drawing, and then a shape like this, you pack this, and you have a shape like this, and you have a shape like this, right? And you pack it like this and you say, okay, now I found a super shape. And then you can say, well, how many of these super shapes can I fill into the grid? And maybe you can do 95% of it. And now you only have to solve like the last 2 or 3. Like, how do I fit the last 2 or 3 into the thing? Then it becomes a much more like solvable problem, right? So again, look at all the fun math. It is very hard to solve these problems. Just to be clear, I hope that you'll get that out of it. These are hard to solve. So given that, let's go look at what everyone says. We see okay, very trolley problem. Looks super hard. I had to do it efficiently, but then all the actual input case turn out very easy. Either there is physically not enough space, or there's so much free space it must be possible. Okay, good. I'm not the only one that got trolled or felt like it was a troll problem. Yeah, I think they're doing just the same thing, right? They're just checking and saying which ones are hard. There you go. I suspect I am not the only one that did this way. And this is, I think this is what's cool about puzzle solving, is sometimes the puzzler says, oh, I'm going to send you down the path, and the path is going to be surprising, right? Okay, someone found a funny threshold where you don't even have to parse. You just look at this area sizes. Uh, yeah, okay, there you go. Yeah, I think okay, so it sounds like it was just trivial to solve it if you, and it's okay if you had to peek. This is a very hard problem, right? I am 100% okay with you saying I had to look for help with this problem because it is absolutely hard. And again, just to be clear, some of the best minds in computer science and in mechanical and computer engineering have looked at this problem to try and solve it, and they have said this is a hard problem to solve. That, so for me, that's what led me down the, okay, well, let's find out how many of them are actually hard to solve. I happen to have like know about the packing problem. I didn't know about this article. This article was new to me, so I went looking for something that might kind of be useful for you to read after if you're looking for something to fall asleep to or whatever. But yeah, it's totally fine to say I just don't know how this would be solvable. Let's see who else. Okay, they were trying to solve it visually. Is like, could it actually be done? Yeah, I think once you figure out like how to solve it, it just becomes absurd. Uh, Again, this is a fun one where if the presents weren't very big, you could like I've seen people before like cut out the shapes and see if they couldn't make, like I was saying, sometimes you can make like super shapes that like are perfect squares or perfect rectangle or very rectangular, and then you make the problem harder. And I've seen people do this manually, and I think that's totally cool, right? Like imagine like you're cutting it out, and I've done this before. Like I think I had a problem a while back where you were folding a shape, and now you had to like you had a rectangular grid and suddenly you had a 3D cube, but the where you traversed was based on the 3D cube. I had to do some weird I actually cut out a piece of paper to fold it to see where they connected because it wasn't just visually mathing to me. So I think this is a cool idea, right? Is to say, oh, I'm gonna actually see if I can't like do some visualization of like how do I put these pieces together and stuff like that. Very good. Uh, okay, what? This person actually tried it. Oh, it says it runs in 40 seconds. Rotate, flip all orientations. What is there? So let's find out what their tree. It. Okay, so this is a quick check to say like if there's no more space left, it won't fit. This must be 40 seconds for the for the sample. I don't see them doing anything specifically cool that would allow them to solve this for the entire input. Because what I'm doing is bit masks backtracking, but I'm actually doing it with uh, a heuristic as well, right? 40, I could see it taking 40 seconds for the sample input. So maybe that's what they're saying. That would make sense. There you go. So I told you, I think I tried a couple of them. I was like, oh, wait, is it zero? Because I had my math wrong. So I was like, wait, is the actual answer zero? Yeah, there you go. Perfect. Nope, I think this is the right way to go about it. Yeah. Like a Packer thing is very hard and it takes a long time. Again, because you're doing a lot of the search space. So we'll look at the main page. I fell for the trap of looking at Reddit before getting my solution again, but it's figure you don't brain. Yeah, okay, there you go. Perfect. Yep, complexity. Think about like the branching you have to do, right? It is very hard. And so we only have 7 again, I think I've said this multiple times. We only have to place for part 3 to say there's no solution. We only have 7 boxes to place, and each of them only have like 3 to 8 rotations. But that combination is literally like quadrillions of checks, right? Nice and kind to humanity. This, oh, this is their solution. Okay. Yeah, you just test. Does it do the thing? Okay. We all got trolled. Well played. Yep, I agree. Very trolly. More effort parsing than solving. The parsing actually wasn't too bad because, I mean, if you look at my parsing, it is a bit odd. I didn't even try and clean it up, right? I said to myself, okay, well, let's do a from for a shape where we just skip the first line and then collect the rest of the things. And then for a region, we just split by this. We split by this and then by this. And what I said was, okay, get me all of the chunks. And then I know all of them, but the last one are shapes, and the last one is the region. So the parsing didn't actually turn out to be that tough, at least for me. What is this? Oh, that's funny. That's definitely not the sample input. Yeah, exactly, right? The old sample input. What a crazy troll. And it's great. I love it. I love it. Yeah, when I did the math on the input, that's the thing you got to realize is like when you're looking at these, it's one thing when it's 7 times 8 times so 7 times 8 factorial or whatever. That's already huge. Now imagine this one. It's like uh an infinite number of guesses. I did jokingly think like, okay, I've optimized it to this many milliseconds. Can I take the ones that are like trivial and see if I can't actually solve them? Meaning there is a solution, I just have to find the right one. Still never finished. Took forever. And that may be my own frailties or whatever, but I suspect it's a pruning was more than enough. There you go. Yeah, there you go. I wonder what they did. So one of the things you can check again is like do the area check and just say, oh, does it solve? It solves. The hardest one is to say it's never going to work, right? Oh, I guess that's true. If your algorithm is do both of these, and obviously if it's easy you put yes, if it's an area fail you put no, then you like skip all of the other code you've written, right? Okay, so I that does make sense. Yeah, you just skip. You've written like 500 lines of code to try and solve this problem, and the only code that's interesting are the 2 blocks that check like the early exit cases, right? What a troll. It's great. It's great. I love it. What a great end to the year. uh Okay, let's look at some of the memes. Let's refresh. Uh, what's happening? Must have been the way that I control clicked or something. Uh, Yep, exactly. There is no rest. Today was ruined for me because this morning day 12 spoiler approach showed up on my feed. I'm not subbed to hear Res algorithm put it on my feed because I've been sub really fun, but having spoiled. Oh, that's a bummer. I would say here's what I've learned for these AOCs. If you're on Facebook, Twitter, Reddit, I guess not Twitter, X. I don't use most of these. Um, and you want to solve these puzzles, do not look at them. I have not looked at any social media until I solve the problem. For this specific reason, is I don't like to get spoiled. Oops. I don't like the spoiler type thing. I don't, I want to actually have the fun of trying to solve it. And if I fail, then I can come solve, right? If it's not working, then I can come try and solve it. Um, but that is a bummer that it got spoiled. There you go. Very good. Very good. I actually, again, I know we don't want to talk about easy or hard, but it did kind of feel like this a little bit. That being said, a lot of it has to do with me just having solved a lot of problems recently. That helps a lot. How could I, Z3? I don't have any idea. Oh, this is an interesting one for Z3. I actually don't know if Z3 will do bidding problems really well. Oh, this is actually a great troll right here. Try pruning trivial cases out of your mind. Those where you have too much space or those where you have clearly enough space, then you can optimize the remaining case. This is perfect. I don't know. I'm enjoying it too much. Okay. Every day under second. That's pretty good for Python. Very good. Very good. I think all of my days are definitely under like 10 milliseconds. I was looking. This one won't show up well. I think I had. Let's see. Where can I run this? Maybe right here. This one won't show up super well, but you can see some of them are in like the 3 milliseconds. This one's 6 milliseconds. 5 milliseconds. Right. So, and I didn't include day 12, but I felt pretty good about this year that I was able to get all the solutions into the, tens of milliseconds. Yes, very much. Thank you. This was a fun year. Eric is his name. Okay. Lots of fun. Do some AI art. Okay. So this is the normal 2D bin packing problem. Is like you go you again, it's DP, so you try and place a bunch of them where they can be placed, and then you're slowly trying to like iterate. I realize this is like skipping over, but you will spend a lot of time down here and very rarely switch pieces up here. It's a known hard problem, so you have to do a lot of this. So my self-respect. Okay. Wait, why your self-respect? This is so dumb. Yep, that was it. In theory, I don't think it was so dumb though. I think he says dumb as in like, okay, I got trolled. But what what a great day. I loved it. Loved it, loved it, loved it. Okay, let's see if there's any more fun memes. I don't know what's happening with my tab here. First year I've finished. Oh, the timings. Okay. Part 1, day 12. Very bueno. Some of these are in the second range. That's still really. I bet they're using like Python. Python. Yep. Perfect. Those are great times, especially for Python. That's awesome. Very good job. Very cool. Uh... Oh, it's cool that people are actually trying to pack them. This is what I'm saying is like if you've ever seen these puzzles, you can actually kind of do some of them by hand and you can start to reason and see patterns and it becomes kind of fun. This bad boy can fit so many. Okay, yeah, that little U shape. There you go. What to do now? Everybody codes. Donate. Yep. Decode. Eco CTF. Yeah, there's lots of fun other things to do. We've got a lot. Maybe that's where we should conclude here. There's lots of fun stuff to do still left. We got puzzles unsolved, puzzles I've long forgotten that we need to solve. I do want to do the Z3 thing, kind of show you how that works, just so I think it's a cool thing to have in your toolkit because you obviously you don't want to like say, oh, I can just Z3 everything, because there are quite a few that are like constraint problems that are solvable with Z3, and you might want to like try and branch out more. But I do think it's a valid solution, so it's worth having it in your toolkit, learning a little bit more about it. So we got lots of stuff to do in the channel, but if you have ideas, please let me know. And you know, if there's some of these puzzles that you want me to do, I'd be happy to try them out. Especially if I get trolled. Maybe that's the great troll debate, right? So anyway, send them your way. I've had a lot of fun. It was a great year. Thank you very much to the puzzlers. I know it's a lot of work to do this, and so I appreciate like just being able to solve these puzzles. Lots of fun, and kudos to all of them for all the hard work they do. We'll call that a wrap. Thanks, everybody. Talk to you next time. Bye.